Welcome to Operations Research. Today we are diving into the Hungarian method, a brilliant mathematical recipe for assigning resources to tasks in the most efficient way possible. Whether you are matching workers to jobs or drivers to passengers, this algorithm guarantees the absolute best assignment without wasting any time or money. Before we look at the math, let us understand why this concept matters. Imagine you and your friends are splitting chores, and everyone has different skill levels. How do you decide who does what to finish fastest? The Hungarian method solves this exact everyday dilemma. It is a combinatorial optimization algorithm that finds the perfect one-to-one match between agents and tasks. Instead of guessing or trying every single combination, which would take forever, this method guarantees the absolute lowest cost or time in polynomial time. Now that we understand what the assignment problem is, let us look at how mathematicians write it down. This formula represents our goal. Z is the total cost we want to minimize. The variable C sub ij is the cost for a specific worker to do a specific job. The decision variable X sub ij is 1 if the assignment is met and 0 if it is not. As the cost for a specific pair increases, the algorithm naturally avoids it by making X sub ij equal to 0. This ensures the cheapest possible one-to-one matching. This formula we just saw leads us to an important question. How do we actually find that minimum cost? The core principle behind the Hungarian method is the concept of opportunity cost, which is the extra price you pay for not making the absolute best choice. The algorithm uses a process called row and column reductions to subtract the smallest numbers, creating zeros in our cost matrix. A zero represents a perfect assignment where there is no extra opportunity cost. The algorithm then tries to find a maximum matching of these zeros. Now that we know the principle, let us outline the exact steps you need to follow. Step 1 is to subtract the smallest number in each row from every number in that specific row. Step 2 is to do the exact same thing for each column. Step 3 is to draw the minimum possible number of straight lines to cover all the zeros. If the number of lines equals the number of rows, you are done. If not, step 4 is to adjust the matrix using the uncovered numbers. And step 5 is to repeat until you find the optimal solution. Before we move on, let us see this with a concrete example. Suppose we have 3 workers and 3 jobs, and we need to assign one worker to one job to minimize the total cost. We start by writing down the initial cost matrix to organize our data. The numbers in this grid represent the cost for each specific worker to perform each specific job. Our goal is to systematically reduce this matrix to find the cheapest possible one-to-one matching. Continuing with our example, we perform the row reduction. We find the smallest number in the first row, which is 9, and subtract it from every number in that row. We do the same for rows 2 and 3. Next, we perform the column reduction on this new matrix. The smallest number in the second column is 1, so we subtract 1 from every number in that column. The other columns have a minimum of 0, so they remain unchanged. Let us visualize the next step. You're looking at a fully reduced matrix. We need to draw the minimum number of straight lines to cover all the zeros. We draw a vertical red line down the first column and horizontal green lines across the first and third rows. It takes exactly 3 lines to cover all the zeros. Because 3 lines equals our 3 rows, we have reached the optimal solution and can make our assignments. Now that we have verified our matrix is optimal, we can make the final assignments. We look for rows or columns with exactly 1 0. Worker 2 only has a 0 for job 1, so they get that job. Worker 3 gets job 3. This leaves job 2 for worker 1. Looking back at our original costs, we add 9, 8, and 10. The total minimum cost is 27. Sometimes the basic row and column reductions do not give us the optimal solution immediately. Let us look at a slightly harder example where we must adjust the matrix. Suppose we have 4 contractors and 4 projects. We write down our initial 4 by 4 cost matrix based on the given costs. We need to find the cheapest way to assign exactly one contractor to each project. This will require us to use the matrix adjustment rule to create new zeros. We will start with the same initial steps we used before. First, we perform the row reduction by subtracting the minimums 10, 5, 12 and 14 from their respective rows. Immediately after that, we perform the column reduction by finding the smallest number in each column of the new matrix and subtracting it. This gives us a new matrix filled with zero cost opportunities. We are now ready to test if this matrix can provide a perfect assignment. Now we try to cover all the zeros with the minimum number of straight lines. We can cover them using one vertical line down the first column and 2 horizontal lines across the first and fourth rows. We have covered all zeros using only 3 lines. Since 3 is less than our matrix size of 4, this indicates that we cannot make a perfect assignment just yet. We will have to adjust the matrix to find the final answer. To adjust the matrix, we look at all the numbers not covered by any lines. The smallest uncovered number is 2. We subtract this 2 from all uncovered numbers. Next, we look for intersections, which are places where 2 lines cross. These happen at the top left and bottom left zeros. We add the 2 to these intersection points. All other covered numbers stay exactly the same. This crucial step creates new zeros for us to use in our next matching attempt. Now we try to cover the zeros again in our newly adjusted matrix. It now takes 4 lines to cover all the zeros, which matches our matrix size of 4. We have reached the optimal solution. We assign the contractors to the projects based on the zero locations. Looking at the original costs, we add 5, 15, 15, and 15. The absolute lowest cost possible is 50. Now that we have solved these examples, let us look at why this matters in the real world. The Hungarian method is incredibly important because it prevents massive wastes of time and money in complex systems. When you request a ride on an app like Uber, the system uses a variation of this method to assign the closest available driver to you, minimizing the total waiting time. Hospitals use it to assign nurses to different wards based on skills, and airlines use it to assign flight crews. Without this tool, companies would face severe inefficiency. Let us review the key takeaways from today. The Hungarian method is a powerful mathematical tool for solving the assignment problem. By systematically reducing rows and columns to create zero-cost opportunities, it guarantees the most efficient matching between resources and tasks. Whether assigning workers to jobs or drivers to passengers, this algorithm ensures that the total cost or time is kept to an absolute minimum. You have now mastered a fundamental algorithm that keeps our modern world running efficiently. Great job!